All right, to begin today, we're going to just review a little bit of yesterday, those three equations that we came up with, show you just a little bit more about them, and try to get you just that much more familiar with what they do. Like I told last hour, the problem with these equations is you can absolutely go to the homework right now and you can absolutely plug and chug in numbers and you can absolutely still have no idea what these equations actually do, full plugging and chugging. So that is what I want to focus on right now. It's not what the numbers are specifically, but kind of how they particularly work. Let's begin with this guy right here. I told you yesterday that this guy is basically the definition of the radian, which is partially true. Specifically, it's the radian if this is what? Let's go back a different ways. Let me draw a circle. What is this on a circle? Arc length. So what would this have to be in order for it to be a radian? What would arc length have to be? How far around the arc length would I have to go in order for that to be a radian? Is this a radian? No, that's more. So essentially, if delta S was what, you would get a radian? The size of? There it is. In other words, if delta S was R, you would get delta theta equals R over R, meaning delta theta is 1 radian in that case, and that would be this guy right here. Okay. So maybe a better way to say this is not that this is the definition of the radian, but instead this is an equation that translates a linear distance, an amount of space, with an amount of angle. To help us out on that particular front, I'm going to do something to this equation. Very simply, I'm just going to do a small amount of algebra. I'm going to multiply r over here. And you would get delta S equals delta theta times r. Yes? What would those numbers be? Again, let's think about this visually. If I was just looking at a full circle. All right, let's go back to my picture here. Let's go back to my circle. If we were dealing with the full circle, let's draw this out. Here's delta S for a full circle. What is that? No, hold on. That's the circle. That would be the arc length. That's not that, what you're telling me. What does that represent? There's a name that we already have for the arc length of a full circle. Circumference. So S would be circumference. Now this is the question that you were about to answer, but I want to make sure I put the right things in the right spot. What angle, what radial angle, 6.28, or what would math usually say? 2 pi. So that angle for a circle is, does that look familiar? That's simply the equation for circumference. Circumference is equal to 2 pi r. So what's different about this guy and why we use it? Well, this is a one specific circle. This guy is every possible amount that we could go around whatsoever. Does that make sense? Okay. The conversation that we had a lot yesterday, which I'll have again, is going to come from this guy on a wheel. Like imagine this is your wheel. I did this yesterday. And the wheel moves around this much delta S. If the tire doesn't slip, if the wheel doesn't slip, then we would say it's going to go some distance. And how do those two numbers compare? They are equal in that case. Now, let's give some, for instance, where they would not be equal, okay? Because usually they will be for our purposes. Delta S or arc length will be equal to delta X for most cases. Like if, let's draw another picture. Let's draw a zoomed out picture. Here's my car. This guy is this wheel right here. Basically, if the car travels a certain amount of delta X, like if the car travels a mile, all I'm trying to get you to see is, okay, if the car travels a mile, how far do the outside wheels got to go? 1 mile. Delta X was a mile, but so is delta S in that case. Here's a case, though, where that wouldn't be the case. If there was slipping, like take for the fact that it's winter. You're driving along in the winter and you hit an ice patch. and you hit the brakes. Now, good brakes actually still roll. That's called anti-lock brakes. We're not going to worry about that now. We're going to think about crappy brakes. Crappy brakes hit, and they lock up. Okay? In that case, if they lock up and still slide, are these two numbers the same? No. Which one's more in that case? Delta x would be much bigger. Delta s in that case would basically be 0. Okay? What would be the opposite of that? See if you can't figure out in your group, 20, 30 seconds. What would be the opposite of that? I think I already said it, so I don't need to keep going. What is it? Burnout. In a burnout, you lock out the car so that it doesn't go anywhere. You spin the wheels, in which case, which number is 0? Delta x is 0, but you get some delta s in that case because apparently you want to ruin your tires for whatever particular reason. All right. Fair enough. So, the first equation that you have to understand is this one. As a matter of fact, this is how I'm going to start to keep showing it to you right here, even though it technically started as this guy right here. As a matter of fact, in your work, I don't care if you start on either spot, just make sure you notice here it's dividing, here it's multiplying. How do I know the difference? Well, honestly, just a real quick unit analysis is going to help you. That's got to be meters, yes? That's got to be radians, which I think we mentioned yesterday is technically a no unit, so this almost is unitless. So what does that have to be? That's got to be meters, and it has to be on top. Here you got meters divided by meters, which gives us radians, or actually unitless in that case. So think about that so your units match to make sure you have the right equation in that particular case. But let me give you another example. Okay. I want to be able to have you compare this guy to these two equations. So I'm going to put them up here real quick. These are the other two equations from yesterday. Okay, and I said I was going to talk about that t today, and I will be talking about that t today, but it's not quite yet. Okay? Imagine Spainor is going to spin around in a circle. All right? So as you think about this, make sure you're kind of viewing this ideal from a top-down view. So let's go top-down view. Okay? Yeah, all right, fair enough. Okay? And let's say my fingertips out here are going to travel a total of, making up some number here, let's just go 8 meters. Okay, it's going to go 8 meters. What do you need to know in order to know how far I'm going to spin around? Radius. Okay. So, center, fingertips. Let's give you an easier number than is right there. I got like 88-ish in this case. So 90 centimeters just to make your numbers a little simpler. So my radius is 90 centimeters. How many times do I spin around? Go. I'm going to need to do some calculations and write some stuff down. By the way, before you get too far, what is 8 meters in this example? Which variable? Delta S. That is how much space my fingers are covering, or how much arc length my fingers are covering. And of course, what's the 90 centimeters? That would be radius in this particular case. I stole numbers from last hour, so if I'm not mistaken, the correct answer is 1.41. Yes? How are we feeling about this? Cool. Like I said, numbers are great, but I want to give you a visual of what the heck that means. On the way to 1.41, you got the number 8.88. Yes? What is that? What was 8.8? What are the units on that? Number of radians, or another way to say that, but you're 100% right, is the amount of radiuses that you go around. So again, to visibly show that, here we go. Here, hold on, let's use a different color. Here we go. Here is 0.9 meters. Here is another hold on, I'm not matching it up well. Artistic skills are terrible and all that, so I'm trying to do my best. Okay, there's 1 meter. Sorry, there's not a meter. That's 0.9 meters. That's another 0.9 meters. That's another 0.9 meters. There's another 0.9 meters. There's another 0.9 meters. There is 6.9 meters. How many 0.9 meters will fit in a full circle? 6.28. So of course we keep going around, switching colors here so that you can kind of tell the difference. Here is the 7th, one right there. Here is the 8th, right there. And then you get about 8.88, so right about here-ish. So how many times did it go around? 1, and then about 40% of the other one in that case, because there are 8.88 radiuses that fit, and therefore we go around 1.4 times. Essentially what you just did is simply use that equation right there. Yes, you took 8 meters by figuring out how many radiuses divided by 0.9 to get 8.88 radians or radiuses, and then of course you divided by 2 pi radians in 1 revolution to get 1.41 revolutions. Fist to 5, how we're feeling about that? Cool beans? I like that that's a big number. I just want to make sure, I'm sure you guys were all good, want to make sure that that like visual is there. Let's enter in these things, okay? I'm not going to talk about numerically, but what if we looked at my elbow in that amount of time? Discuss in your group, if this number stays the same, what would happen to the answer for the elbow? Discuss. So if my elbow is going to travel 8 meters, question is, how many times would I spin around? Then, what would happen to the answer and why? Discuss.
It's a smaller radius. It goes around. It takes more distance to go. Like it has to go around more times to cover the same amount of distance that the arm had to go around more times to get it smaller.
All right, what happens to your final answer?
Increases.
It increases. It increases because, I think it was said over here, the radius got smaller. So do I have to go as far to go through a full circle? No. Whereas before, it took me, what was it, something like 6.28 times 9. That would be something, what is 6.28 times 9? 6.28. So my circumference of my fingertips is something like 5.65 meters. Obviously, that's not nearly as far for the elbow. Hello. All right. Now, let's do this. I spin around, okay? Do all parts of me have the same velocity? Careful with this. Velocity, VT. Do all parts of me have the same velocity? Are all parts of me, here's the way you want to think about it. I tried to mention this yesterday. I'll say it again. When I say just velocity, you're looking at how much space is covered. Do all parts of me cover the same amount of space in the same amount of time? No. You just got done having that conversation right here. Which one is going to have a higher velocity out of my elbow or my fingertips? Fingertips have to go faster, okay? Which one, so will all parts of me have the same angular velocity?
Yes.
Why? Sure. Can you say that a little differently? You are right. I just want to make sure we're on the same page.
Like all like in a line on the same point. They're like changing that angle.
So let's look at my elbow and my fingertips, okay? Go through a full circle to make things easy. Okay, starting with the first one. Why is the velocity of my fingertips bigger? Cover more space. Correct. Covered. We just said 5.65 versus like 3 point blah, blah, blah. Whoever knows what the radius is not important. But do all parts of me have the same angular velocity? Yes. Why? Same amount of angle. My numbers again were, my fingertips were 5.65 to something 3 point whatever in terms of distance in whatever time it was. But what was the angle of both of my fingertips and my elbow in this particular case? What angle did both of them go through? 6.28 radians in that particular case. So they have the same value while these are different. What I tried to end with yesterday, and I think this example will probably help, okay? Actually, let's do a different one first. Imagine a merry-go-round. Now, by the way, just as a heads up, because this always gets confusing every single year, there are 2 types of merry-go-round, and it feels like whichever one I'm thinking of, usually, for whatever reason, you're thinking of the opposite. So there's the merry-go-round on the playground, yes? And then there's the merry-go-round with the horses. All right? So, I think it's okay, we have strong feelings about that. Okay? Just as a heads up, some people in the past, having known this from talking to them, think that that's also a merry-go-round. So, okay, I hear you. I will make sure to be clear on one way or the other. Let's begin with the carousel or the horsey swap. All right, you're next to somebody on the carousel.
Yeah.
Okay, you go around. Do you have the same angular velocity? Do you have the same velocity? Discuss real quick.
Angular, yes, velocity.
Sounds like you're good. All right, new example. New example. You're going around part of a turn on cars. Okay? We did. But we're going to do something slightly different. This time, we're going to have two cars sitting right next to each other. If two cars are sitting right next to each other on this turn, they're right next to each other at any point in time, what has to be the same, what has to be different between, let's call this car 1 and car 2? Angular has to be the same. This equation comes from this right here, right? Essentially, that does what you just said. They have the same angular velocity, so who has to be going faster? All right, that's the easy part, so let's flip it. Let's make it a little more challenging. Now, in this case, let's say the cars are limited by their physical ability to produce speed, meaning they are now going the exact same speed around, and they're not drifting in and out, they're staying at the same spots. What does that mean the same, and what's different, and which one has a greater of which one? Okay, between these two again. Start with the easy part. Which ones, what value is the same for both of them? They're going the exact same speed, so they have the same velocity. Discuss in your group which one's going to have a larger angular velocity, or is it going to be exactly the same? Discuss quickly. Be right back after these messages.
Wait, are they still matching like next to each other?
No, they're not inherently doing that. They couldn't by staying at the same speed.
Wait, no. The inside does not have a greater angular velocity. Because it has shorter time to cover. So then it's going to take 1 hand. Yes, because it
Who has the larger angular velocity, 1 or 2?
1.
1 is correct. The visual representation is this. If I draw the exact same distance for both of them, if I draw the exact same distance, who has gone through more angle?
1.
1 has gone, even though they've covered the same amount of space, they've covered the same amount of space, so they have the exact same VT. It's basically this equation with a little bit of algebra. Angular velocity is VT divided by R. If they have the same velocity, whoever has the larger radius will have the smaller angular velocity in this particular case. Here's the last example of this that I think is pretty easy. Okay, the Earth goes around the sun. Is the Earth moving fast? Okay, well, I got to get specific here. Does the Earth have a very large velocity?
Yes.
Yes, it's going insanely fast. Does the Earth have a very large angular velocity?
No.
No, it's ridiculously tiny. You could actually calculate the Earth's angular velocity. Do that now.
What?
Calculate the Earth's angular velocity. Real quick, let me help you out with this. Whenever it comes to angular velocity, this is the equation right here.
Oh, I got you.
Yes?
I got you.
Okay? The thing that we always can do this with is, unlike velocity, we always set this number to be the same thing, and we probably know what time goes with it. AKA, what number do you always set this guy to be when figuring this out? 6.28, yeah, or 2 pi. Here's what I'm saying. Do you know how much time it takes for the Earth to go in a circle? Then you know that's 2 pi, and that is what? 65 days, which of course you'll have to get to seconds.
Oh, that's a lot of seconds.
You'll be okay.
We talk about speed, not like spin.
Angular velocity.
It is precisely 5.47 times 10 to the negative 10.
It's tiny. 365 times 24 hours. times there's 3,600 seconds in an hour. So there are 31,536,000 seconds in a year. Take 2 pi divided by that.
I got the wrong answer.
2 times 10 to the negative 7.
Yeah.
Does it make sense that we don't cover very much angle of the circle?
Yeah.
Yeah, it's a gigantic circle. So we don't go through very much of it, even though we are going incredibly, incredibly, incredibly fast at that time. What is the only information you would need from me, by the way, just using this equation a second ago? What's the only information you would need from me in order to know how fast we are going? You would need to know, we wouldn't call it radius per se. It is the radius, you're right. What most people would not call it radius.
Difference between like distance from us to the sun.
How far it is from us to the sun.
Yeah.
Yeah. Which is?
At least 2.
At least 2, agreed. I don't know if it's memorized off the top of my head. I have a lot of ones, but distance from us to the sun.
Really far.
I'm cool.
Well, I don't like it in million. I don't love it in miles for you guys. Let's go 150 million kilometers. How fast are we going in meters per second? It's 150 million.
That's a lot.
150 times 10 to the 6 kilometers. So let's do this for you. Remember that would be, let's go 9. Just make that 150 times 10 to the 9th meters.
Okay.
How fast are we going is the question. That is 150 billion meters.
Oh, yeah, I forgot.
Does anyone have the right answer? You might remember that we actually calculated this earlier this year.
I also don't.
Roughly speaking, if you did it correctly, it should be 30,000. 30,000 meters per second. Or essentially what you just did was this. 1.99 times 10 to the negative 7 radiuses per second. How big is one radius? 150 billion meters. So multiplying those out, you should get that we're traveling at 30,000 meters per second in order to pull that off. All right, how are we feeling about this? Again, the big 3 equations are this guy, and I didn't block that one off, but you get the general gist. This guy right here. Most importantly, out of this conversation, and I'm trying to hit this in repetition, is understanding that this is a change in orientation. This is a change in, this is a change in space over time. Let's talk about that t real quick. Where did my wheel go? Why the heck have I been discussing this as vt? Well, here it is. Velocity, you said yesterday, is delta x over delta t. We just got done saying in this example, well, that's unhelpful. There we go. In this particular example, that would be how much delta x the car travels in a certain amount of time. But this right here said that the arc length is going to have to travel the same distance as the car. Yes? What is vt? This stands for velocity tangential. Or this is the velocity of the outside of the wheel. If there's no slipping, what would you guess that the velocity of the outside part of the wheel is relative to the velocity of the car? The same, because it's going to cover, if that's delta x and that's delta s, and they're the same amount, are they both going to be doing it in the same amount of time?
Yeah.
Yes. In other words, if your wheel is going, if your car is going at 60 miles an hour, guess how fast the outside part of your wheel is going? 60 miles an hour. Cool. All right. The hard part of that process is this. Let's say your wheel is spinning counterclockwise. What's the direction of the velocity at this part of the wheel? Which way is this part of the wheel? Like you have like a speck of dirt right here. Which way is it going? West. What do you mean west? How about left, champ? All right. How fast is the bottom part of your wheel going? Same speed, right? But is it the same velocity? Because it's going to the right. Correct. All right. That'll be helpful a little bit later. All right. New stuff. Here we go. I've got a car. As a matter of fact, no. Instead of the side of a car, we are going to look at the top part of the car. Still a car. The car is going to be going to the right now. It's traveling at a particular velocity. I put VI because the question is, tell me one thing that the car could do to accelerate. A little bit more specific in terms of the numbers. More specific.
It can change more in the
Speed up. Cool job. Yes. Go fast, me. Words, numbers, more. Yes. All right. This would be the visible representation of that. Its final is now bigger than its initial. Yes? Okay. So, what in this picture does this arrow represent? Correct.
That was quick.
Cool. I know this seems simple. It will be until it's not. Let's do it again.
Makes me feel uncomfortable.
Sorry, my apologies. Starting from a similar spot, what is something else that the car could do that would
Turn.
accelerate? We're getting actually the hard part of that. Let's do the easy one first. Brakes. We could slow down, in which case this is VF, and this represents the change in velocity. I highlight these two simple examples that hopefully all of you do consider simple because I want to point out that in this picture, I can represent change in velocity by drawing a vector from the end of the initial to wherever the final represents. Yes? Okay, now in that, what is acceleration?
Change velocity over change.
So it is basically this vector here divided up into how much time it takes. Yes? So if you started, say, for example, at 11 meters a second, and you ended at 20 meters a second, what's your change in velocity? You would get 9 meters per second plus. Yes? If I then told you it took you, I don't know, 2 seconds, you could go, oh, well, I found that the difference is 9 meters a second. It took 2 seconds, and so my acceleration is 4.5 meters per second every second. Or, of course, you usually shortcut that to 4.5 meters per second squared. Yes? Here's the thing. Here's the rub going to where you guys were trying to head a second ago. If this is my initial velocity, and this is my final velocity, what just happened to my speed? According to that picture, I'm not trying to be terrible with my picture, my speed did not change. Did I accelerate?
Yes.
Best visual representation of that, what I was trying to get to, is boom, there's my change in velocity right there. All right, now here's the issue with that. Am I going to be able to use this equation to calculate that? According to this equation, we use the same thing. If you remember, what did we use to find the change in velocities? Well, technically we used speeds to find the change in velocity because the direction stayed exactly the same. So let's talk about something that will come back a little bit later. What is, picture-wise, what is a way that I could change this picture and increase change in velocity? What could I do to this picture to increase the size of that arrow? So two major things. You could go faster. Oh, okay, I want to change not just final velocity because that would change speed.
Oh, both.
We don't want to change speed. So the first thing I could do is this. If both of them go faster, but we stay at the exact same direction, you can see that both of them are in fact faster. Yes?
Yeah.
Will I get a greater change in velocity?
Yes.
Cool. What is a second thing that I could do to that if I don't change the speed that would give me a greater change in velocity? Turn more. Sure. So I wanted to look at this pictorially first, but we will come back to this at the very end. The goal to show you is that you could see visibly, yep, the two ways I could change the velocity are, I could make it go faster, or I could make it change more angle in the same amount of time. All right. So, when do we get what I'm talking, what change in direction? Well, if you were going a particular direction and you were going to start changing direction and you continuously changed direction, what shape would it make? What is it? Shape always going to be made if you consistently change the exact same amount of direction. Correct. So one of the best ways to look at our examples is to think about examples that go in circles and what's going to be different about them versus what we've been dealing with. Well,